The last 50 years has seen a truly transformative advance in our understanding of the world around us. I wish to try to illustrate just how transformative this is by first describing what we knew about cosmology, the study of the large-scale nature of the universe, 50 years ago. But I think it's well to first set the stage for orders of magnitude by drawing your attention to this galaxy of stars nearby. It's shaped very much like that of our own Milky Way galaxy. It's a disk rotating. You see dark lines where interstellar dust has settled into densities high enough to obscure the starlight. The clouds of dust get strung out by the differential rotation of the galaxy, producing this elegant spiral pattern. You can see blue splotches here and there where interstellar gas has settled and formed stars. In a population of young stars, the most luminous of the stars are by far the most massive are by far the most luminous. These massive stars are very hot. Their surface is blue. That makes the blue light you see here and there. Around the blue light, often you can see red light. That's where ionizing radiation has ionized the interstellar gas. The plasma, in recombining, makes a characteristic hydrogen line, 6,000 angstroms. You see the red glow. You see near the center a yellow glow, more uniformly distributed. That yellow glow pervades throughout the whole of this region. It's the light of some 1,000 million stars with masses similar to our sun. We know from our neighborhood of our galaxy that there are at least as many planets around stars as there are stars. So it is a very good bet that in this galaxy there are some 10,000 million planets on which all sorts of wonderful things are happening that we, the members of the human race, will never see. 50 years ago, it was common to assume that the galaxies are uniformly distributed in the large-scale average. This, an idea from Einstein. Somehow we don't know whether he was right for the right reason or not, but he was. 50 years ago, however, we knew that the visible nearby galaxies are much more strongly concentrated in the northern hemisphere than the south. Doesn't look at all uniform. There was some reason to think that the distribution may be uniform on still larger scales by counting the number of galaxies seen as a function of how bright they are. The less bright the galaxy in the sky, the further away. The inverse square law tells us that the number of galaxies you count should increase as you decrease the brightness to which you count, according to this straight line, the theoretical curve. The data taken by Edwin Hubble in the 1930s, to an optimist, follows pretty closely, and to a skeptic, doesn't follow all that closely, but it was at least encouraging. There are a lot more faint galaxies than there are bright, as you'd expect in a uniform distribution. In the early 1960s, there was a revolution with the recognition that some galaxies, on very rare occasions, explode violently, send out jets of rapidly moving plasma that make these pools of plasma and magnetic field that make very strong source of radio radiation. These exploding galaxies are visible in the radio to immense distances. This map of the nearby, of the most luminous couple of hundred of the exploding galaxies shows a few effects that I have to explain. First, don't look at this hole in the center. The telescope couldn't reach that part of the sky. Don't look near this point. That's a very luminous nearby exploding galaxy. The telescope gets confused nearby. Look elsewhere, and what do you see? Nothing. This was Einstein's vision. Of course, it's not a demonstration that the universe is uniform in the large-scale average, but I'd certainly count it as encouraging. We had the notion that the universe is expanding. Here is an illustration. Imagine we live in 2 spatial dimensions, not 3. We live on the surface of this balloon. You must not ask yourself, what about the surface of space above or below the balloon surface? You're not supposed to think about that. You live on those 2 dimensions. the balloon is being blown up. You're not expanding, and galaxies are not expanding, but the distance between galaxies is increasing. Now imagine that you sit on one of these galaxies and you look around you as the balloon is blown up. You'll see that the galaxies are moving away from you. You may say, the universe is expanding and it's expanding away from me. But of course, if you live in this galaxy, you'll see the same thing. Nearby galaxies moving away from you, further galaxies moving away more rapidly. An elegant arrangement. Everybody thinks they're at the center of the universe because there is no center. In this expanding universe picture, the prediction is that the recession velocity, which you measure through the Doppler effect, increases in proportion to the distance. This was a discovery paper in 1929. Distance increasing to the right, recession velocity measured by redshift increasing upward. Pretty schematic in the discovery paper, but by the mid-30s, this linear relation had been mapped all the way out to 1/10 of the velocity of light. Pretty impressive. In fact, until the 70s, the maximum distance to which this has been tested only increased a factor of 3. Photographic plates had reached about their level of capability. It wasn't until digital detectors of the sort that allow you to take all those photographs with your cell phone improved things a lot. We did not understand in the mid-60s masses of galaxies and clusters of galaxies. Here's a concentration of galaxies. It looks like a galaxy. It's a galaxy of galaxies. But the important thing is, already in the 1930s, the astronomer Fritz Zwicky was pointing out that the motions of these galaxies relative to each other were so rapid that if the mass of this system were that of the stars seen in the galaxies, then the thing would be unbounded and fly apart. Certainly doesn't look like it's flying apart. We did not understand masses at all in the 1960s. The question, how will the universe end? How did it begin? Was debated with very little evidence anyway. Some, such as Georges Lemaitre, who was the first person, I think, in the late 20s, early 30s to thoroughly understand the relativistic theory of an expanding universe, felt that the universe likely exploded from a dense state. He liked to call it the primeval atom. Other people later came to call it the Big Bang. On the other hand, Fred Hoyle, Tommy Gold, with Herman Bondi, postulated another sort of universe. Imagine that as the universe expands and the galaxies move apart, matter is continually spontaneously created. The matter gathers into galaxies, of young galaxies, to replace the old ones moving apart. An elegant picture. You see it reflected in the inflation cosmology for the very early universe. And of course, you could certainly say maybe it's something entirely different. So that was the situation. The start of the transformative development came in 1965 with the recognition of the sea of radiation that was discussed. It was proposed then, now well established, is a fossil from the early universe, and as we've learned a lot. Just a bit of history about this idea. It goes back to the Russian refusenik in the 1930s, an early refusenik, George Gamow, a brilliant intuitive physicist who in the 1940s proposed that a hot universe, starting out very dense and very hot, might, as it's expanding, create the heavy elements, create the elements through nuclear reactions in that very hot early plasma. He worked out many of the details with his student, Ralph Alpher, on the right and Robert Herman on the left, the notion of element formation in the early stages of an expanding universe. This universe would have been hot in the early stages. A key feature of heat is thermal radiation. You've all held your hands next to a bonfire and felt the warming radiation. If you have a cavity whose walls are held at a fixed temperature, the radiation will be produced inside the cavity, and the intensity of the radiation at each wavelength will be determined by the temperature of the walls. You tell me the temperature, I'll tell you the intensity at every wavelength. By the way, you might remember, if you're of a certain age, And in those days, we lived under the grotesque threat of mutually assured destruction, the Soviet Union and the Western states. This cartoon took note of Alfred's thesis on the origin of an expanding universe. The caption, 5 minutes, say, for mutual destruction as well as creation. So nothing much came of this idea until the 1960s, when my teacher and thesis advisor, Bob Dicke, liked to ask us on occasion, so what was the universe doing before it was expanding? His idea, which he liked a lot, was that it was bounced. The universe collapsed, expanded again. It's interesting that Gamow had proposed the same thing. Here's a quote you might read. The Tolman in the 1930s had proposed the same thing, a bouncing universe. It's something that people liked. But Bob added something critical to that. He, a consummate physicist, emphasized that this is an idea that might be tested. And really interesting ideas are those that can be subject to a test. This development came in the old physics building at Princeton. In the attic, we were crowded. When Bob gathered together his young research associates, Peter Roll, Dave Wilkinson, and me, explained an idea about a hot Big Bang. Just to take a minute to review his ideas. When a star, the stars, like the sun, is shining because elements of hydrogen are fusing together to make the atomic nucleus of helium. The binding energy released is shown as starlight. Formation of one helium nucleus releases something like 1 million electron volts of energy that comes out in about 1 million starlight photons. Each of those photons is redshifted and made less energetic as the universe expands. If the universe contracts again, those million photons get bluer and bluer, more and more energetic, and if the collapse is deep enough, a couple of those photons with energies around 1 million electron volts will be sufficient to dissociate that nucleus and leave you with a leftover 1 million photons. That is to say, you have made entropy big time, a highly irreversible process. The entropy, of course, is the thermal radiation that Bob proposed might be present. And he suggested to Peter Roll and Dave Wilkinson that they build a microwave radiometer to look for this radiation. And he told me, with a wave of the hand, why don't you think about the theory? Peter went off to work in education with computers. Dave and I just hung around and formed a career out of those casual remarks. Bob Dicke knew a lot about microwave radiation and its detection. In war research at the MIT Radiation Laboratory, he had invented this gadget called the Microwave Radiometer. He had traveled with it to Florida to study the effect of atmospheric water vapor on radar for the purpose of going to shorter wavelengths to get better spectral resolution. In Florida, where the air is full of water vapor, he measured the radiation from the water vapor. And as a side result, he wrote that the radiation coming in from cosmic matter is less than about 20 degrees Kelvin, a convenient measure of the energy of the radiation, and also, of course, if it's thermal, that's its temperature. The actual radiation is at 3 degrees. He came close to measuring it. If he had brought his apparatus back to MIT or to Princeton and made the measurement on a cold winter night when there's very little water vapor in the air, you might imagine he might have detected the sea of radiation. But he had other things on his mind. It took a while to get around to that. Here we are back in 1964. Here is David Wilkinson on the right, Peter Roll in the plaid shirt, with a Dicke radiometer they had built for the purpose of looking for this radiation. As it happens, there was 5 years earlier at the Bell Telephone Laboratories in New Jersey an experiment in communication with microwave radiation. This was an important forerunner to the sight of our students wandering around campus staring at their cell phones. It also produced a curious result. This looks like an informal arrangement. You see the planks or rough wood, but the telescope was very carefully engineered, as was the detector inside, and the engineers had gone to great trouble to track down all sources of radiation in this whole system. They ended up assigning the equivalent of 2 degrees to radiation that had snuck into the horn reflector antenna from the ground. This horn reflector antenna, again, had been very carefully engineered not to emit radiation from the background. They had to put this radiation somewhere, however, and they put it at the antenna. Here, an article a year later by Ed Holm saying, commenting on the temperature, radiation produced in the instrument, and in particular, radiation coming from the low, back, and far side lobes, creeping into the antenna from the ground, are estimated to add only 2 plus or minus 1 degrees to the system. This estimate is based on the temperature not otherwise accounted for. In short, the engineers had to balance the books. They had to say that radiation was coming from somewhere. Let's assume it came from the ground, even though that exceeds the temperature expected from similar antennas. 1963, Bob Wilson and Arno Penzias at Bell Telephone Laboratories wanted to use this technology to do astronomy, but as written here, they decided they needed to resolve the uncertainty surrounding the seeming extraneous sources of system noise encountered by several of our Bell colleagues. In short, the Bell people had this constant irritation. They were getting more radiation than they expected from their communications experiments. What was that radiation coming from? These people did a brilliant job of eliminating every possible source of that radiation within the telescope or from the ground, from nearby cities. They were completely blocked when they heard about this experiment through a lecture I gave. The first lecture I gave on this subject at a colloquium in Wesleyan University in Connecticut was mostly having to do with the question, how much energy and radiation is there coming in space? For a broad range of frequencies, we have bits of information about how much radiation there can be. I had also noted the idea that there might be thermal radiation left over from the Big Bang, 3 degrees, maybe 30 degrees. And I had a point here that puzzles me, 3 centimeters, an upper limit. Here at another colloquium a couple of months later, 6 centimeters. I don't know what I was doing with 3 to 6, and I don't know where that came from, but one had limits. No, I got no feedback from the Wesleyan colloquium. From this one at the Applied Physics Laboratory, a friend from high school, from graduate student days, Ken Thurner, attended, told Bernie Burke about it. Here is Bernie a few years later at MIT, along with Alaire Tourmé on the left, and George Clark on the right. George? Yes. Bernie told Arno, you guys ought to get in touch with the Princeton people. Arno called Bob, as Paul explained, and we had the possibility of a great discovery. Here is a graph I made shortly after the news came. Here is wavelength increasing to the right. Here is intensity, units, energy per frequency interval times frequency interval, which I think I might have pioneered. It's the energy per logarithmic interval of frequency. We knew about radio galaxies, of course, and they introduced some radiation coming in from outside the Earth. But the point was that this line extrapolates to well below the intensity of the radiation the Bell Labs people were obtaining, if in fact that radiation was coming in from outer space rather than somehow a source on the ground. There is also radio radiation from starlight, but it's a way down. In short, we already knew right away this is something new, and that was exciting, of course, because you have a new phenomenon, something new to measure, and something new to make theories about. I gave a lecture on this idea at the American Physical Society meeting in June of that year, a tidied-up version of this, of course, and I remember a polite reception, but also a very distinct feeling, lots of luck. You're making a big deal about 1 point. But soon the Princeton experiment was finished, and we had a second point. It certainly looked good. Soon, people were working on making measurements at other frequencies. As you go to shorter frequencies, atmospheric water vapor becomes more and more troublesome. A way around that is to go to a high site. This is Climax Observatory in Colorado. Here is Dave Wilkinson on the left. Here is Bob Stokes. And here you might recognize Paul Boynton. And by the end of that decade, about 1970, I was able to show this figure showing wonderfully well that the energy as a function of frequency follows the long wavelength part of the curve real well. You notice, however, a horrible thing here, an apparent detection of a lot of radiation where the spectrum ought to have turned down. In this book, which I wrote in 1970, I was very cautious about this notion of having detected thermal radiation from the Big Bang. The chapter on it was labeled, "Is this radiation from the Big Bang?" Pros and cons listed. It was clear we had to measure over the peak. The technology to do it was to use something called the Fourier transform spectrometer. Here, Herb Gush, 1973, a first attempt at that, failed. Here, the following year, a proposal to NASA, Dave Wilkinson and others. I'll point out John Mather in a moment. And here, in fact, is the COBE team as it assembled, the NASA satellite mission. Dave Wilkinson again, John Mather, then a young postdoc who agreed to take on the job of principal scientist for the experiment. A terrible gamble. This is going to take 10 or 15 years for the project to develop. He then watches the instrument, a fuse, you light the fuse, and the thing explodes, and if all goes well, it flies high up in the air. If not, it explodes. And he's left with respect from a few colleagues, but no papers. His career is really in trouble. You have to be a strong character to stand that, but he was able to stand watching it lift off and produce brilliant results. Meanwhile, here's Herb Gush, and here are his two able colleagues, Mark Halpern and Ed Wishnow. I have to admit that whenever I look at this photograph, I have to smile and ask myself, if I didn't know these guys had done something great, if all I knew about them was this image, would it inspire confidence? But in fact, after 15 years of development for these two projects, 1990, they both produced these results. The rocket experiment from Gush, Halpern, and Wishnow has higher noise than the beautiful satellite experiment of Mather et al. But still, you saw both establish the point, this spectrum is wonderfully close to thermal. I must admit, a personal note, that it annoys me, probably more than Gush, Halpern, and Wishnow, that young people, the movers and shakers of today in this subject, by and large, don't know about this measurement. It's just got lost. I know of no moral to that story, except that we're human, and we develop all kinds of legends. Here's the state of the measurements today. This solid line near the top is not a theory, that's a measurement of spectacular precision. Here are other measurements. Notice the long range of frequencies. The theoretical curve you can just make out running well through the observations. A glorious piece of evidence, I would say an iconic piece that shows tangibly that the universe had to have evolved from a different state, because this is a thermal spectrum. Our universe as it is now is transparent to this radiation. There's no way it could force the radiation to relax to this thermal equilibrium. The universe had to have evolved from a state in which it was dense and hot enough to have relaxed to equilibrium and then expanded away from it. In short, this one slide is a powerful argument that our universe is not as it is now forever. Our universe is evolving. It's a profound note. Our universe is evolving, and a profoundly simple yet deep piece of evidence for that. Well, we have other pieces of evidence. Let's look at another fossil from the early universe, helium. Here, a conference on cosmology and astrophysics in 1953. Here, the organizer, Walter Baade. Next to him, George Gamow, I spoke of earlier. Here in the background, Margaret and Jeff Burbidge. And still further back, Don and Irene Osterbrock, I'll mention. I guess I should point out that this young lad, Ed Spiegel, took the photograph by setting up the tripod and then running back and getting in line, thereby gaining a place in the front row. In Gamow's lectures at this summer school, Gamow showed the results of a computation of his idea of a universe that started out hot and rapidly expanding. As it cooled, nuclear reactions produced lots of helium. This by mass, roughly 30% by mass helium, the rest hydrogen, and a trace of deuterium, the heavy isotope of hydrogen, and helium-3, the heavy isotope of helium, or the light isotope. And the same year, in another paper, the interesting point to notice here, this high production of helium and in good agreement with the observed relative amounts of hydrogen and helium in our universe. It was a remarkable statement because no other astronomer knew that the helium abundance in the universe is high. Somehow Gamow had convinced himself, I don't know how, that helium is abundant. But as time went on, people started recognizing that the helium abundance is remarkably high. Here, a paper by Jeff Burbidge. He was at the conference. He could have, maybe he attended the lecture and forgot, maybe he didn't attend Gamow's lecture, but in his discussion of this puzzlingly high helium abundance, he did not mention Gamow's idea that the helium could have come from a hot Big Bang. Don Osterbrock also was at the conference. He did attend Gamow's lectures, he remembered them, and in this paper, pointing out still more abundant evidence that the helium abundance is high, around 30% by mass, and he pointed out the origin of these could be understood without difficulty on the explosion formation picture. I don't know why he called it the explosion formation picture, but he has a reference to Gamow. This, I believe, is of great historical interest. This is the first time someone proposed actual detection of a fossil from the early universe. It was not recognized as such until after the radiation was discovered. But we should remember him. Meanwhile, you remember I had been, with a wave of the hand, instructed to go think about theory. Here is bits of a paper written in 1964. Deuterium and helium production in a hot universe. I didn't know about Gamow then. I was reinventing the wheel. Here, of course, in the same paper, helium production in a cold universe. Who knew? Is the universe going to prove to be hot or cold? I soon learned that I was reinventing the wheel and set out to make a better wheel. In particular, here is the amount of production of deuterium and the amount of production of helium as a function of how hot the universe is. The hotter the universe, the further you are to the right. If the universe is very hot, then when conditions were right for thermonuclear reactions, the density of baryons would be so low that nothing would happen. You'd have no helium, no deuterium. If the temperature is very low, then the density, when conditions are right, is high, and you make a lot of helium. You burn all of the deuterium to helium, so you don't make any deuterium. But as you increase the temperature, you make more and more deuterium left over because you're lowering the density, and you're making slightly less helium until this very dramatic transition. In short, one could see that if you could measure the helium abundance and the deuterium abundance, you had a pretty strong check on what's going on in the early universe. Now, I'm leaping ahead a bit. This is the present situation. We have very good measurements of deuterium abundance in young galaxies by looking at galaxies that are in front of quasi-stellar sources that are very bright, and you see absorption of the quasi-stellar light at the resonance line for hydrogen in the foreground galaxy and for deuterium. Wonderfully well detected, deuterium and helium measured, deuterium and hydrogen measured, and put to good use, as I'll describe in a while. Meanwhile, yet another test for cosmology. How did our universe grow clumpy? It is, of course, distinctly clumpy. Here's an illustration. This is a section of the sky about that big across, looking up toward the pole of our galaxy where obscuring gas and obscuring dust is not very important. You see the clumpy distribution of matter, and of course you also see something else. This part looks a lot like this part. You're seeing hints of the uniformity on large scale, and you're seeing the texture of our universe in the matter distribution. The data for that map were taken by Donald Shane with his assistant Carl Wertman by hand, taking 10 years to scan photographic plates of the sky with a scanning microscope and recording where the galaxies are. They produced a set of data sheets this thick, a copy of which I have in my office. And these bright young people, with a couple more, Jim Fry, Ray Siniera, Mike Seldner, turned to the mighty power of new computers. Before that, what did you do with the million numbers that Shane had recorded by hand in those pile of data sheets? Nothing. Yet they took the data so carefully that when computers came along, we could make that map and show it to Donald. And I had the distinct pleasure of asking him, so is this what you saw? And he laughed and said, I was looking at this one galaxy at a time. We also had another excellent map of the very nearby universe. Here is Professor Fritz Zwicky. Here are a set of volumes mapping out the nearby universe. Here is a map of the distribution of galaxies in the very nearby universe. The other was a much deeper sample. Fritz Zwicky had his little ways. He did not suffer fools gladly, and he had a very low threshold for detection of fools. But I was therefore quite pleased that when I sent him this map, he sent a polite letter of thanks. To my eternal regret, the last time I had to reorganize my office after reconstruction of the building, I somehow lost that letter. A polite letter from Fritz Zwicky is something you treasure. Now we could turn these maps into measures. 2-point correlation function, angular separation. If you don't know about 2-point correlation functions, you can breathe easily for a while. Well, I'll explain. This is Zwicky's sample. It is very strongly clustered. That is a big correlation function. Here is the Donald Shane's sample. It is smaller because you see clumps on top of clumps. It averages out the correlations. This is still deeper sample obtained in Poland, the Jagiellonian field. And one knows how these guys should scale with distance and put them together to a scale invariant to a distance independent measure. One had consistency of the measure as a function of depth of the sample, indicating that we had a reliable measure of clustering. Very important, which we could try to put together with a reliable measure of how the radiation is distributed, asking yourself the question, if the matter grew clumpy, what did the clumpiness of the matter do to the radiation? Should make it irregularly distributed to some degree. A long series of experiments searched for this radiation. Here, one in 1965 by David Wilkinson again and Bruce Partridge. It was not on this site, but rather next to it here in the top of the geology building. I remember with pleasure that this flap, which switched the antenna from the equator to the pole, had a hinge. The hinge got rusty. The hinge started squeaking at night, and one night some annoyed students scaled the wall of the geology building and oiled the hinge. What people will do. What do we see here? Some Paul Point, you'd already moved to Seattle with Bruce Partridge. You had used this instrument to put a level, a limit of 0.1% on the fluctuations of temperature across the sky. The radiation is really smooth, but there were another 2 orders of magnitude to go. Here, the somewhat later measurement from a balloon. What most strikes me about this image, does it to you? The hairstyles. This was early 70s. Ed Cheng on the right, Peter Salson. Yes. Ed Groth. Ed Cheng, Peter Salson, Dave Wilkinson. Pleased to meet you. And the latest version, the Planck satellite mission, European Space Agency, a spectacular piece of equipment. But you know, what pleases me is that these big horns around the edges are using this invention, Dicke's radiometer. And isn't it charming? Notice output meter. When was the last time you saw an output meter in a space experiment? And here they saw. This is the texture of the microwave radiation sky, this radiation left from the early universe. You must understand that the mean intensity has been subtracted out. These are the departures from the mean, and they are on the order of parts in 100,000. Tiny fluctuations. Now the big question becomes, can we make a theory in which we account for the development of the clumpy distribution of matter and its effect on the distribution of radiation that matches both the distribution of matter and of radiation? So let us get excited about that. Well, here it is, just a comparison. We know how the matter is distributed. We know the radiation is distributed. Let's make a theory. Making a theory requires, of course, theory. I guess that's probably obvious. And in particular, this theory requires two hypothetical, I emphasize hypothetical components. We add them in by hand because we need them. One is dark matter. That is to say, matter that doesn't interact with anybody but gravity. And Einstein's cosmological constant lambda. A side remark, lambda is now known as dark energy, a triumph only of public relations because we don't understand lambda any better now than when it was known as lambda. Here is the Abbé Georges Lemaitre, the one who, as I said earlier, best understood Einstein's general relativity and the theory of the expanding universe in the late 20s, early 30s, with Einstein and Millikan of Caltech. And just a note on the evolution of this name and on the meaning of this figure. Einstein, in 1917, at first proposed the universe is homogeneous. He had his theory of general relativity, and he supposed, as a given, it's obvious, the universe is forever. It doesn't change. The universe, you and I change, the universe doesn't change. So he had to arrange that the gravity that's trying to pull together the material in the universe is balanced by something. That balance is contained in this equation, in this term. That term is allowed to be there, not required. You can put it in or not, and you can let this value of lambda have any value you want. Here is the term that represents matter distribution. Here's Newton's gravitational constant. It's also a number. You can put in whatever you want, but you better put in the measured value. On the other hand, we don't have a measurement for lambda. You can put in what you want. The proposal of Einstein was that the lambda term, which tends to push matter apart, just nicely balanced gravity, which is trying to pull matter together, making a stable, static universe, which of course is what the universe ought to be. It was Lemaitre who noticed that this balance is unstable. Push the universe a little, and it'll expand. It was that realization that caused the great Professor Dr. Willem de Sitter at the Leiden Observatory in the Netherlands to write in a newspaper article, what, however, blows up the ball? What makes the universe expand or swell up? That is done by the lambda. Another answer cannot be given. Lambda was pushing the universe apart. You see now the origin of this symbol. The artist, who did a brilliant job otherwise, got lambda backwards. But in fact, soon, De Sitter and Einstein recognized that we don't need lambda at all. And we don't need space curvature. A simple universe. I love this photograph. De Sitter, looking pretty skeptical, decided, let's make the universe as simple as possible. No cosmological constant, no space curvature. Here's an illustration I made of a coincidences argument back in the early 70s. The situation is this. Time is increasing to the right. This is a really long time ago when the universe was tiny. Here is a measure of how big the departures from a universe that just has escape velocity, kinetic energy of expansion, just balanced by the gravity of mass. And one notices that, of course, you can have the balance exactly mathematically perfect, and you will stay right along this balanced line. If you make the density a little bit higher than pure balance, then eventually the universe will collapse. That's a bad thing. If the universe collapsed when the temperature was already 10 to the 10th degrees, we wouldn't be around to think about it. It could be that the universe goes into free expansion there if you're a little bit under the critical balance. That's an equally bad thing. We wouldn't be around if the universe were freely expanding, no gravity to make matter collect into galaxies to allow us to thrive. This is a good thing then. Imagine that the balance is almost perfect and we live at no particular time. Here are the curious coincidences, that the balance is broken just as you and I came on the scene to marvel at the fact that the balance has been broken. A ridiculous coincidence. This idea, I think, played no role in Einstein and De Sitter's deliberations, but in the 1980s and 1990s, it was deeply influential, and many of the most profound and careful, but maybe not totally sensible people in cosmology were convinced the Einstein-De Sitter model is the only reasonable possibility. That kind of reasoning, I just take liberty to point out, is common. We all make assumptions that are really based on nothing but, well, to be blunt, prejudice. We don't stop and look and ask, on what basis am I making that judgment? For in fact, there was no evidence for Einstein-De Sitter. Even worse, there was some evidence against it. Measurements, they can be very healthy. And in particular, this was the first all-sky, reasonably large survey of the redshifts of galaxies. It showed us a couple of important things. Maybe here I'll pause to note one of them. Here are the bright galaxies and here are the faint galaxies. Or is it the other way around? Notice how the big galaxies and little galaxies are very similarly distributed. It struck me from the beginning as a wonderfully curious thing, big and little galaxies similarly distributed. The other interesting thing that came out of this is that the galaxies aren't moving very fast relative to each other, so that if matter were distributed like the galaxies, and if the mass density were that of the Einstein-De Sitter model, then the galaxies would be moving much more rapidly than is observed. The alternatives were that the mass density is lower than Einstein-De Sitter, at the time a profoundly stupid remark, or that matter is more smoothly distributed than galaxies. But if matter were more smoothly distributed than galaxies, then why in the world are the distributions of bright and faint galaxies so similar? Surely, if galaxy formation is favored where the density is high, then galaxies that manage to form where the density was low would bear the stigma of an unhealthy youth. But they don't. Now we come again. Remember, I'm working on how structure formed. And here is a simple illustration made by my colleague Ed Groth, and somehow we lost the caption. Oh well. Numerical computation, but here is on the upper left is a sphere of particles moving apart in accordance with Hubble's law, redshift recession velocity proportional to the distance. Here it is at a later time and still later time. to illustrate better what is happening, expand this distribution and contract this distribution so they have the same mean size. Now you look at this and you notice a very distinct difference. The universe is growing from smooth to clumpy. It's a profound fact, and one that seems to be well established now. Our universe is close to uniform in the large-scale average, but it's growing more clumpy. It was in the past much more smooth. A profound notion, really, and I think one that we must pay attention to. Gravity is causing material to gather together. A treatment of how this gravity operates is perhaps best illustrated by an elegant demonstration of a resonance. I have here an empty bottle. You remember what happens when I blow on it. Resonance. The time it takes for a wave to get down to here and up again, giving us the period that is so characteristic of that. A bigger bottle, lower frequency. A boundary condition. Another illustration of boundary condition. Here I have a plate of plastic. I shook it and I took a photograph. You see the bumpy waves. It looks chaotic, but you see also it's not chaotic. See how they tend to line up with the boundary. So in the early universe, hot, matter is thermally ionized. We have a plasma. The free electrons scatter on the radiation. The free electrons pull on the protons through electrostatic fields. The result is matter and radiation act like a fluid that is viscous, but a fluid. Departures from the uniform distribution of that fluid are important because there's a high pressure in the fluid due to the provided by the radiation. That means that the distribution of the fluid starts oscillating. The oscillation ends when the radiation reaches a temperature of 3,000 Kelvin. The matter is released, and whether or not you have a concentration or whether the density is higher than average or lower than average depends on the phase of this oscillation back and forth. The result is that you receive bumps that are favored in the intensity of fluctuations set by the resonance condition on what you are doing when you hit decoupling at redshift 10 to the third. I might notice here Dave Wilkinson yet again, Jerry Yu, my first student, and graduate student, and Bob Dicke. Happy times. So what do we got? Again, an illustration, the transfer function. Some wavelengths are favored, some strongly disfavored. If you remember about Fourier transforms of sine functions and cosine functions, you realize that these oscillations produce bumps, which are now observed in the autocorrelation function. Anyway, here was an attempt to synthesize all these bits and pieces. You notice it says, 2 groups have discovered large-scale irregularities in the microwave background, departures from uniformity. One of them, a Princeton group. Well, I had to pay attention to that, so I made a theory. The Princeton group soon withdrew its detection and lowered the limits substantially of how large can be the departures from uniformity. So a beautiful theory. I'm sure people would have come to love and respect it, except it's wrong. So in frustration, I introduced the cold dark matter model. You are not intended to read these, except to understand that they're there. There are papers, in which the key point, I found that if I introduced this notion of cold dark matter, it would help a lot in reconciling the measurements of the matter distribution and the limits on how much the radiation distribution can depart from uniformity. In 2 papers, one introducing the cold dark matter, the other Einstein's cosmological constant, I stress that when this paper was introduced, when this notion was introduced, it became popular, in large part, I fear, because it was simple to analyze. That's not an argument against something, but it's also not a terribly strong argument for. At the time, there were lots of ideas about what kind of universe we're in. Here, Joe Silk and I, a 1990 review, different possibilities. The details, not at all interesting, but there were lots of possible solutions. CDM, the cold dark matter, was most popular, but I think for somewhat irregular reasons. Anyway, data again came to the rescue. And here, I should emphasize that this detection of the wiggles in the distribution of matter are not from this historic map, but rather from a deeper, better one made by the Sloan Digital Sky Survey. But the point, the oscillations are detected, characteristic of the resonances in the cold dark matter model. Even better, of course, is this detection of the resonances in the microwave background radiation, an exquisite fit to the theory. And in fact, such an exquisite fit that one can, from this figure alone, and under the assumption that the universe is cosmologically flat, deduce such things as the mass density in baryons, the mass density in cold dark matter, Hubble's constant, and so on. A beautiful fit of theory and measurement. But at this point, you would be well advised to hold onto your wallet before settling any bets, and to recall that bright young theorists can be wonderfully inventive. And if you give them a measurement, they can be very clever at finding a theory that fits it. After all, I did it with fallacious detection of anisotropy. How much would you bet that given this figure, these data alone, bright young theorists can invent a theory that will fit it? The theory allows 6 free parameters, and you all recall von Neumann's statement, with 4 parameters I can fit an elephant, and with 5 parameters I can make its tail wag. It is important there, deeply important, that you have other tests, and in fact I've already mentioned one. This is looking at waves in the distribution of matter relatively close to us, whereas the radiation is showing us distributions that are produced, were impressed on the universe. Oh, where am I? Forget it. The CMB was released from the matter back at very high redshift, great distance. The matter distribution is measured locally. You're measuring it at different places by different methods, very different possibilities of systematic errors, and yet you're getting a consistent result. Here, another independent check. This shows the brightness of supernovae of a particular type as a function of how far away they are. This, the theory with the 6 parameters that were fitted by the microwave background anisotropy, fitting these data to spectacular precision. This beautiful measurement, in an earlier version, netted a very prestigious prize for these 3 guys. Adam Rees, Saul Perlmutter, I'm batting Saul and a good friend in Australia. Adam Rees. Brian Schmidt, thank you. I love this photograph. The founder of this prize, Sir Run Shaw, made a vast fortune in entertainment, is well respected in Hong Kong and mainland China for his charitable work, support of education, and of course he supported this prize just to support science. See his suit, bespoke. It fits him like a glove. These guys are neater than I've ever seen them, but nonetheless, they're not quite in the same class of dress. Anyway, a brilliant measurement that fits the others. Lots of other measurements. Now, let's go on. Many more. I will have a little time now to relax to comment on a side issue. No. I've forgotten how long. Let's spend another 5 minutes on this point. This is an essay written by Thomson, Lord Kelvin, a little over 100 years ago. At the time, Lord Kelvin had every reason in the world to be absolutely confident that his physics of electromagnetism and mechanics is solid and reliable. He owed his fortune and his peerage to income from patents for transoceanic telegraph cables. He knew darn well his physics is well established, but he saw 2 clouds on the horizon. Those 2 clouds, of course, were predecessors of quantum theory and relativity theory. Now, it's important to emphasize that when his his electromagnetic theory was supplanted by the quantum version, his descendants were not required to give back the income from those patents. That electromagnetism is as good as it ever was, but it is incomplete or a limiting case only. So must it be, or may it be, with our cosmology, our theory of the expanding universe. We know it's a good approximation. We have a sufficient number of tests, I think, to convince us of that. Yes, the universe has evolved from a dense state, and the evolution is well described by general relativity theory. But there may be clouds that will indicate that there is a still better theory to be found. Cloud 1. Again, the Abbé Georges Lemaitre, observing that Einstein's equation can be rewritten this way so that this lambda term acts as if it were part of the stress energy tensor of the world. In particular, it would be a zero-point energy filling space. It's interesting that Lemaitre tried on occasion to persuade Einstein of the merit of considering this term. A letter from Einstein to Lemaitre, 1947, I thank you very much. Since I've introduced this term, I've had always a bad conscience. But at that time, I could see no other possibility. I cannot help to feel it strongly, and I am unable to believe that such an ugly thing should be realized in nature. That is the cosmological constant. Also in the 1930s, that was later, Wolfgang Pauli, the great Austrian physicist, in a magnificent survey of quantum physics, points out that zero-point energy of quantum physics is absolutely real. You leave it out, you get the wrong binding energies for molecules. Zero-point energy is real. Zero energy is mass. That was assumed then, is now well established. Mass gravitates. That's very well established too. But the electromagnetic field, which in quantum physics is nothing but a set of oscillators, has therefore to have real zero-point energy. The only problem with that argument is that the zero-point energy adds up to absurd amounts, just ridiculous. Pauli therefore wrote, it is evident that this zero-point energy can have no gravitational effect. So embarrassing, but he didn't know what else to say. Now the binding thing is this zero-point energy, if in a Lorentz covariant theory, is nothing but the cosmological constant except with an absurd value. And here we sit, a cloud on the horizon that looks pretty dark. I offer another cloud. Here, I deeply respect the work done at this university on galaxy formation, but I remain convinced that galaxies have a lot to teach us. Here is that galaxy I showed before. Here is an exploded version of the very center. You notice that these dust clouds spiral in all the way to a tiny little star cluster here, mass 1 million solar masses, but that's on this scale tiny. The dust settles to the plane. The dust obscures the starlight in the plane. The fact that the dust is obscuring starlight all the way to the center tells us that this is a remarkably flat galaxy, okay? Flat. Here is another galaxy nearby, happens to be seen sort of close to edge on. You look at it, what do you see? You see a rough surface, but remarkably flat through the center. That is very curious within our lambda CDM theory, because here are simulations, pure dark matter, no baryons, showing plotted in yellow, the material that's now within 3 kpc of the center, which is to say about half the distance we are from the center of our galaxy. Where was this matter now near the center back at redshift 1 or 3, back when stars were forming rapidly? You see it scattered all over the place on very large scales. It's easy to imagine that as this material gathered together, it formed a galaxy and that the gas settled into a disk that is rotationally supported. But what do you do about all the stars that were forming back here? These stars are forming in lumps. When you assemble the lumps, where do those stars end up? Not collected in a disk. They'll move through the disk to form a stellar bulge or halo. But our stellar halo is tiny, a few percent of the mass. How in the world did you get to make these pure disk galaxies? It is, to me, a really serious problem. What is the origin of the problem? Maybe the complexity of gravity physics, of baryonic physics. But I think, without a doubt, it's easy to imagine that the problem is in the dark sector. Our model for dark matter is too simple. A guess. I can't resist pointing out another curiosity. Here is the map of all known galaxies out to a distance of, well, 8 megaparsecs, or about 25 million light years. There are some 277 galaxies in this region in orthogonal views. In this big slice of the region, there's one galaxy. There's another one known, but not yet studied. Why the enormous empty region? And here is this little galaxy. Here's a space telescope image. Can you see that the long axis is pointing about like so? Here is atomic hydrogen on the same scale around this galaxy, spread out, and the lines mark equipotentials of constant redshift. You notice how these are tilted to the right. The long axis is tilted to the left. It's a remarkable thing. In short, this galaxy could be studied in a lot more detail. But astronomers have so much on their plate, no one has gotten around to doing it. Isn't that a charming gift for the next generation of astronomers? Well, I'll end here, but one final remark. This vast increase in our knowledge of the way the universe is built was gained by people. I offer some examples, and I'll thank you for your attention.
I think he made it clear why many of his colleagues refer to him as the inventor of modern cosmology. Would you like some questions?
With pleasure.
Would you like to question?
About a year ago, your colleague Paul Steinhardt gave a talk here in Seattle, and the topic was basically inflation has got huge problems, and it causes more problems than it solves. Would you care to have your view of that?
I certainly don't disagree with my esteemed colleague, Paul Steinhardt, except that I think he's hoping for more. All of our best physical theories are incomplete. Isn't that right? Inflation is incomplete. It's more woefully incomplete than many other parts of physics. But it does a pretty good job at telling us a story. How did the universe get to be so smooth? It gives us a nice story for the tilt in the power spectrum. And those two points, to me, argue, well, maybe it's on the right track. Maybe it needs a lot of adjustments for a really credible theory, but maybe it's on the right track. There was, of course, the great furor of the possibility of a third test, the Bicep 2. Would have been wonderful if it had been real. It would have, I think, maybe tipped the balance to making me to take really seriously inflation. That may still happen, but at the moment, it's true that inflation does not have a lot of positive evidence, and it is also true that it's difficult to make a complete theory. As I say, I'm less worried about the possibility about making the complete theory than about testing the aspects that we can test. But we will, of course, see.
Any other questions?
So in the popular media, they keep talking about how they're pushing galaxy formation back further and further, but it's never really clear to me why that's an issue. Can you give some context?
Well, of course, you notice in this simulation, things are happening between redshift 1 and the present. Naturally, in lambda CDM, galaxies form rather late. Because galaxy formation is a complex business, It's hard to translate that into a serious challenge to the theory, but it is a flavor that doesn't taste quite right to me. It will be heavily debated, and it is happening at this university. Very detailed numerical simulations of how the matter gets together, baryons as well as dark, to form galaxies. They make, these days, very impressive looking galaxies, except for that flat part, and that's why I emphasized it. Or Jim.
Another issue is the correlation of supermassive black holes with galaxies.
Yes,
And
yes,
the fact that supermassive black holes seem to exist at very large redshift, which
yes.
has given galaxy formation theories, black hole formation theories, a bit of a problem.
Yes.
I want to comment on that.
Well, you know, one thing, of course, is to notice that this galaxy has a black hole, but no bulge. The Milky Way, you know, it's charming to me to observe the blunt honesty of astronomers. A good astronomer I deeply admire spent much of his career studying the bulge of the Milky Way galaxy. He now agrees that the Milky Way does not have a bulge of old stars. It's flat. Yet the Milky Way does have a black hole. The correlation of bulge with black hole seems believable, but there are exceptions to it. How did the Milky Way form a black hole without forming a bulge? I don't know. The correlation of black hole with bulge velocity, for example, doesn't make much sense if you don't have a bulge. So clearly, the whole business of how black holes grew is a mess. It's complicated. We don't have a coherent picture. I have heard excellent authorities say, oh, it's easy to form a black hole at high redshift. I don't know. To be debated.